everyone to the afternoon session. Before we start, I just have a few quick announcements. A few of you have been asking about the certificate for attendance at the school, which is in your pack. If you need it, it's signed by anyone from the organizing committee. There's a space there on behalf of the organizing committee. We're very happy to sign it, and you can approach any member of the organizing committee, Alessandra, Giovanni, myself, and so on, and Julio, and yeah, so we can all sign it for you if you need that officially. Also, a number of you, just a couple of you have asked and said that in your organization you need to have a certificate that says I gave this poster or I presented this talk with the title as well as attending. We can do that for you. Just let any one of us know and we will ask Louise to make up a special certificate.
So ask Luisa and then Luisa will print it again.
Ask Louise and
Luisa will prepare the certificate.
Okay, so go straight to Luisa. Salamiro, yes. And we can do that. And then lastly, if you have any photographs you wish to share of the activities, Giovanni is putting them onto website, and I have some already I'll give. And so you should see shortly some photographs. Are there some already? Here? Not yet. So you should be able to see some of the photographs shortly. And we welcome any photographs that you have of activities as good memories of the school. So please give that to Giovanni. Okay. It's my pleasure to welcome Daniel Scheeres from the University of Colorado. And he is going to give us lectures on the mechanics of asteroid exploration.
Okay, thanks very much. Okay, first, thanks very much to the organizers for inviting me to come out and give some lectures. I always love coming to Italy, so it's always a good excuse to do this. And what I sort of settled on is today I'm going to talk a bit more about the use of spacecraft to explore small bodies such as asteroids, and what sort of dynamical issues that we need to contend with, and what interesting dynamical environments these small bodies present to us. And then tomorrow I'm going to talk a little bit more from a natural science side and talk about how we can apply principles of celestial mechanics to the study of these small bodies, in particular to rubble pile asteroids, which we think most asteroids are actually comprised of collections of bodies resting on each other. So in today's, I'm going to first give some motivational material and just a little bit of a history and the current description of one particular mission I'm involved with, in particular, the OSIRIS-REx mission. And then I have a series of sort of case studies of 3 different asteroid systems that we've studied in the last few years that I'll try to move through relatively rapidly, but just to give you a sense of how you can apply all of your dynamical systems tools to these interesting environments. So the sort of a fundamental question is, why are we interested in small bodies? And by this I mean asteroids, comets, and the like. And there are really a few specific reasons why. Most fundamentally, we're interested in them from a scientific perspective because these are remnants of the early solar system. They retain material somewhat processed or minimally processed from when the solar system formed. Their orbits themselves actually act as tracer particles that record the evolution of the major planets, according to something like the Nice model. And when we study them, we really study the formational epoch of the solar system. They've also shaped life on Earth by delivering water and minerals in the early history of the Earth, and by causing occasional widespread extinctions due to their impact. We're also interested in them from just an exploration perspective. They're a possible destination for future human missions. As we explore the solar system, they are indeed the easiest bodies for us to rendezvous with, and have been recently seriously considered by NASA for human exploration. And in fact, they've done extensive testings. This is the Project Nemo, where the astronauts go in under water somewhere in the Florida Keys and actually simulate weightless activities in a natural environment, just to become a little more cognizant of what it might take to operate in the very low gravity environment of an asteroid. A very recent one that's cropped up is resource exploitation. We all know that asteroids are full of valuable minerals and water, and technologies for their extraction and use in space are currently being delivered or being developed. And in fact, there are now several companies who are devoted to this, and more than just being a dream, some countries, such as Luxembourg, are actually investing their money into these technologies. It probably still is a long way off, and their probability of success is maybe still low, but this is motivating people. Probably most importantly is from a societal perspective, because these small bodies continually impact the Earth. You can think of shooting stars you see at night, the Chelyabinsk meteorites, and we know that in the past they have caused or contributed to large-scale extinctions, such as the asteroid that took out the dinosaurs. And a practical question for us to ask is, if we see one on a collision course, could we, as humanity, stop it or deflect it? And this is now a topic of very serious study. Every couple of years there's a planetary defense conference, international conference organized to bring together scientists, engineers, and policymakers to discuss these possibilities and how we would react as a civilization. So that is a compelling reason why we need to worry, or why we study these bodies as well. So I can very briefly talk about some past exploration we've done of asteroids. And perhaps the simplest way to explore an asteroid is just to fly by it on a hyperbolic trajectory. And this gives us very interesting information. You can even get the mass of the asteroid, like we did with the asteroid Matilda. We flew by close enough, at a slow enough speed, and it was large enough so that we could actually measure the deflection of the spacecraft trajectory to determine its mass. The first discovery of a binary asteroid was actually from a flyby observation, where they just snapped a bunch of pictures and they happened to catch one with the moon dactyl orbiting around the larger asteroid Ida. Other nations have gotten into it. The Chinese flyby, the Chang'e 2 mission, took some very interesting photos of the asteroid Tutatis recently. And then, of course, the Rosetta spacecraft flew by Steins and Lutetia, not shown. So these are very easy ways of interacting with and getting images of an asteroid. But it's over in a flash of a second, because you travel at speeds from 1 to 10 kilometers per second. So you only have time to take a few images, and the body is essentially stationary during that short period of time. It hardly rotates. So you only see one side of the body. So there are limitations. Because of that, there have actually been rendezvous missions where we go to a small body and we actually take out that excess speed and go into orbit around it. There. And go into orbit around it. And that's an area that I've studied a lot, and it becomes very interesting because the dynamics around these bodies are very interesting. So the first rendezvous mission was the NASA Near-Earth Asteroid Rendezvous Mission. Space Science Mission visited the asteroid Eros. Launched in '96, arrived in '01, and landed on the asteroid in 2002. And I just have a few images of the asteroid. This is a very beautiful shot, and it shows you the complex shape that this body had. Views of two sides of the asteroid, huge craters on the surface, large gouges that run the length of this body. Another interesting shot, and you can see in the distance huge boulders. So that's relatively far away from us. And the Empire State Building, for context, is about this size. So this is like the size of Manhattan, this entire body, and it spins every 5¼ hours. Yet we were able to go into orbit around there and actually carry out a whole series of observations. Another mission of note that happened recently is the Hayabusa Mission. This was a Japanese sample return mission to the asteroid Itokawa. It launched in '03, arrived there in '05, and returned to Earth in 2010 after several major failures on the spacecraft, yet they were still able to limp back home and actually return a sample that they had taken from the asteroid surface back to the surface of the Earth. And this is an image of it during its re-entry phase back in 2010. It also is the first, one of the first or most novel selfies ever taken of a spacecraft in orbit. Here you see the shadow of the spacecraft against the surface of the asteroid. The small shiny bit is a target marker that they used for surface relative navigation. So if you recall the size of the asteroid Eros, given with scale with the Empire State Building, the asteroid Itokawa is much, much smaller, orders of magnitude smaller, and in fact, it's roughly the same size as the Empire State Building, or you could hide it in the center of it if you wanted to. Yet across these two bodies, which, and this is certainly not the smallest body, this is still a relatively large near-Earth asteroid, we find many commonalities that exist from bodies hundreds of meters in size all the way up to tens of kilometers in size. Even though as you go through that range, the orbital dynamics and the issues that you must contend with in order to have a rendezvous mission at these bodies changes dramatically. Here are some images of the asteroid Itokawa. You see it's strewn with rubble. It has smooth areas which are actually regions of constant potential, which implies that finer materials have actually flown down into these smooth regions and sort of somehow distributed themselves to be at a constant potential, even though this is a gravity or a friction dominated material. And you see huge boulders sticking out of the surface, lying on the surface. This is tens of meters across. And the samples that they took went all the way down to a micron scale. This is one of the samples at about 150 microns in size. And what we believe is a body like this is actually a size distribution from the smallest micron bodies up to larger and larger bodies, up to these tens of meters. And in the picture of Eros, those huge boulders in the back, many, many tens of meters, maybe even 100 meters or more. Current mission, the Japanese have launched the second version of the Hayabusa mission, it's called Hayabusa 2. And this is going to return a sample from a different asteroid, the asteroid Ryugu. Here's a rough shape model of it. They'll actually know much better next summer what it looks like, because that's when they rendezvous with it. So it was just launched a couple years ago. Will arrive early summer 2018 and have a sample back to the Earth in 2020. It's a bit larger than the asteroid Itokawa, believed to spin a bit faster, but the shape is not well known. Not even the spin pole is well known at this point. They're doing many similar things to what the Hayabusa mission did, but one interesting aspect that they will also do is they will have a small explosive device that will actually shoot an impactor onto the surface so that they can expose a crater on the surface And later on, they want to come back and actually sample inside of that crater. So even carrying out that very detailed level of trajectory design and implementation is quite a challenge, and is quite interesting. So when we think or contemplate about performing these missions, these rendezvous missions, and hanging out about an asteroid for some extended period of time and actually carrying out orbital operations, you know, the reasonable thing to ask is what are the challenges that we need to address? How is this different than an Earth orbiter? How is this different than us understanding, say, the orbits of the asteroids in the solar system? What really motivates the study of this, from my perspective, is that this small body dynamical environment is, and you can accurately say, is one of the most perturbed orbital environments that you can find in the solar system. And when you want to control a spacecraft in this environment, there are some interesting challenges that you must face. For example, just the effect of the rotating gravity field can destabilize an orbit and cause it to impact or escape in very short time scale. Just the weak solar radiation pressure can actually strip a spacecraft out of orbit around a small body or cause it to impact on the surface. When we couple these effects from these perturbations, we can truly get chaotic orbital dynamics where you're trying to fly your satellite in this regime. They also present very complex morphologies and surface environments, and in the next few slides, I'll just step through some specific examples of what these extreme environments can do to the dynamics, the orbital dynamics of a spacecraft. To start with, we can talk about just these complex morphologies, and what's an interesting idea or problem to consider is how would you want to study, using a spacecraft, a system as like this binary asteroid, which is known as 1994 or 1999 KW4. In this particular asteroid, the size of this main body is just a couple of kilometers. So these two bodies are separated by only like, I believe it's 2 or 3 kilometers. In fact, you could stand on the secondary and actually jump over to the primary because the speeds are so low because the bodies are so small. And we see it's a lot like the Earth-Moon system in some ways, because the moon is synchronous in a roughly circular orbit with the same face always facing the primary body. The primary rotates faster than the orbit, so it's an asynchronous binary. The primary is actually tilted with respect to the plane of this orbit. You can see that in this picture where this is the view from the secondary looking at the primary, and you see this, this not insignificant tilt. Yet the shape of this guy is so oblate that its J2 parameter, roughly speaking, is like 2 orders of magnitude larger than the Earth's J2 parameter. And if you wanted to just consider constructing analytical theories for the motion around a body that distended, we have to remember, even for the Earth, with its small J2, we need to go up to second order expansions to really accurately nail down the motion. So if we have 2 orders of magnitude larger gravity perturbation and many more higher order gravity terms, you have to go so much higher that it's almost infeasible in some ways. And because of this, we've actually developed different approaches or different philosophies of how we address these challenges. Another challenge is just the rotation of this primary body and how it can affect the orbit stability of a satellite that could be in orbit around there. So these are simulations of spacecraft orbits around the Eros asteroid, the target of the Near-Earth Asteroid Mission. And this body rotates once every 5¼ hours. Here I'm showing just the initial orientation of the asteroid, and this is an inertial plot, so it's actually spinning once every 5¼ hours. And what we have are 3 trajectories. The first is just a very stable trajectory. I just started motion in a circular orbit at a given distance away from the body, moving in the same sense as the rotation, and it just so happened that it remained stable, just stayed there just fine. However, if I just change the initial condition by putting in a 45-degree phase offset, meaning instead of starting here, I instead start here in the same local circular orbit, you see that the dynamics completely changes. It goes through 1 rev, gets a huge boost in energy, flies by again, and then actually gets put on an escape trajectory and actually leaves the vicinity of this asteroid with the V infinity probably just on the order of centimeters per second, but still moving definitely away. Conversely, if we just start at a local circular orbit just a little bit closer to the body, we see that we've crossed some line or a different line, and that now it again only barely makes 1 full orbit before it comes back. It gets boosted up, given a lot of energy by the rotating body, and has its periapsis drop so that when it comes back, it actually impacts right onto the surface. So here you see some of the challenge. Within a very small region of initial condition, you have these diverse outcomes. And this is something that we would like to study and understand, and for practical spacecraft exploration, figure out how to stay away or far away from these very sensitive regions of the orbit dynamic space. Another challenge is just from the solar radiation pressure, or SRP, perturbation acting on a satellite as well. And here, this is an orbit where the spacecraft is orbiting about just a point mass. So ideally, it should be a Keplerian orbit. We're viewing this in a rotating frame with the sun always on the left. However, this is at 1 AU, so the rotation is only about 1 degree per day, so it's quite slow. Without solar radiation pressure, this dashed line would be the approximate orbit. However, here, due to the solar radiation pressure effect, and this is just for a nominal exploration spacecraft, you see that this first orbit is highly perturbed and actually swings back and forth in a highly non-Keplerian trajectory before eventually coming in and impacting on the surface of this body. And if you look at it, actually the eccentricity of this body is cycling from 0 to 1, or near 1, back to 0 again. It just so happens at some point it's at unity eccentricity when it's close to the body, and that's when it impacts. So if you just move yourself like 100 meters further out and start in a local circular orbit, it just immediately escapes. So again, we have this very sensitive region of orbital dynamic space. Here's one more example using solar radiation pressure. Here we've managed to get ourselves into an orbit that appears to be stable. It's a little wobbly, but at least it hangs out there. Orbiting around this body. This is the view from the sun. This is the view in the Terminator plane in the side of the body. And here we see that under the solar radiation pressure, the semi-major axis is approximately constant. And you can show that analytically being perturbed by solar radiation pressure without any shadowing. But still the body escapes. And the reason why here is that the asteroid is on an eccentric orbit about the sun, and I've started this orbit closer to aphelion, where it actually can be bounded, but as it travels to perihelion, it again crosses some line, and it actually gets ejected from the system. Final type of complex motion that we can see is when we have a binary asteroid system combined with solar radiation pressure. And this is an example. I'll talk a little bit more about this particular asteroid later on. But this is the asteroid Didymos. And we've placed this guy in an orbit that actually is resonant with the rotation or the orbit period of this binary body. And what appeared initially to be a nice, safe orbit, again, becomes quite chaotic and ends up impacting on the surface of the larger body. So these are the types of interactions and orbital interactions that we would like to study and understand so that we can reliably design spacecraft trajectories to go explore these particular bodies. So how do we deal with these challenges? In an earlier version of this talk, I would then have a number of different ways that we've developed, tools that we've developed to deal with the analysis of these orbits. But I've given that talk a few times, so for this school I'm going to do something a little bit new. So instead, I'll talk very high level about how we've done this in the past, and then give some specific examples, mission examples of how we're dealing with these challenges now. But as I pointed out, the small bodies really present a huge range of sizes, from Itokawa, which is half kilometer long, to even smaller bodies that we wish to explore, all the way up to Eros, which is almost 20 kilometers long. The spin states that we need to worry about vary dramatically, from relatively slowly spinning Itokawa, which had a 12-hour rotation period, to much faster spinning Eros with a 5-hour period, and then the target of the OSIRIS-REx mission has an even faster rotation period of around 4 hours. Other asteroids actually have complex rotation. The asteroid Titanus, which the Chinese spacecraft flew by, has also been viewed many times using radar techniques. And it's known, in fact, we've estimated what its very precise spin state is, and shown that it is truly in a complex rotation state. So there's a huge variety of challenges, shapes and sizes that we need to deal with. For orbital motion, there are some very special regimes of interest. The gravity regime, where the orbit mechanics are controlled fundamentally by the mass distribution and the rotation of the central body. And for the near mission to Eros, this was the prime concern. Solar radiation pressure regime, where the orbit mechanics are controlled by the radiation pressure and to a lesser extent the tidal perturbations from the sun. When far enough away from the body, the Hayabusa mission really fell into this regime. And we can have this mixed regime where both are simultaneously perturbed by gravity and solar effects. And that last movie showing the evolution of that orbit around the binary asteroid falls into that category, where these two effects can actually interfere with each other and cause strongly chaotic dynamics. There are many other issues that can be studied. Cometary outgassing effects, which was experienced firsthand by the Rosetta mission recently. Hovering motion or controlled motion, which is actually the technique that the Japanese have used for both Hayabusa and will use for the Hayabusa 2 mission. And then questions of surface deployment and motion on the surface of one of these small bodies, which raises a whole host of additional questions, which I'll briefly address later on. So despite all these challenges, one important takeaway is that we can always find stable orbits for exploration around any asteroid. But what the appropriate approach to use will vary and can vary quite strongly as we move from one body to another body. So it's certainly not a situation where one size fits all. And you're always driven by the peculiarities and the specifics of the asteroid that you wish to go and explore. And that is a challenge, because it means that if you just want to launch a satellite and go to some asteroid that you only know as a point in the sky without any other reliable information, it's very challenging to design the spacecraft operations before you actually arrive. And you can even make mistakes in your design so that when you arrive, what you wanted to do may not be possible, and you may be compromised in terms of what your mission plan is. So I'll give my own little advertisement. A few years ago, I did write a book sort of summarizing the work that we had done up to roughly 2010 on this problem, where I study a number of specific different bodies in detail and circumstances in detail. So if you are really interested in this, you can certainly find this, that text. So now I'm going to give you a brief introduction to the OSIRIS-REx mission, still relatively high level. And then after that high level introduction, I'll get a little deeper into some of the dynamics, specific issues and ways of thinking about the dynamics in these systems that we've developed. So the OSIRIS-REx mission is a NASA mission. The PI is Dante Loretta from the University of Arizona. The NASA center involved is the Goddard Space Flight Center in Maryland. And the spacecraft was designed and built by Lockheed Martin. And this is a sample return mission. In some ways it has similarities to the Hayabusa 2 mission, but it also has some real differences. And what's shown here is sort of the most important part of the mission, where the spacecraft comes down close to the surface, uses this extendable arm to actually sample some of the material off the surface and then go back to Earth. So I'm involved with this mission as the lead on the radio science experiment, which means that our team is in charge of measuring the mass of the body and the low order gravity coefficients of the body, and then using that information to interpret the geophysics of this particular small rubble pile asteroid. So the goal is to do a sample return of at least 60 kilograms or grams and up to 2 kilograms of the material from the surface of the body, which is its regolith, and it's a special type of asteroid, a carbonaceous asteroid. It's currently, it launched last year, September 8th. It's currently in transit to Bennu. We rendezvous in 2019, maybe even late 2018. The sampling occurs in 2020, and we return to Earth in 2023. So a couple years behind the Hayabusa 2 mission. OSIRIS-REx, of course, is an acronym. It's like a law at NASA, and it's to study the origins, the spectral interpretation, how do we relate what we see through a telescope to what we see in reality, resource identification, what materials are present in these asteroids that we can actually utilize or could utilize in space, security, I'll talk about that in a second, and regolith explorer, just understanding the properties of the surface covering on an asteroid. We are fortunate in that we actually have a shape model for this asteroid, which is accurate to the few decameter level. This is because it was imaged by the Arecibo radio antenna some years ago, and from that they could construct this rough shape model. And we see it's a slightly oblate, but roughly spherical asteroid. So in terms of security, one interesting aspect of this particular asteroid is that it's among the most potentially hazardous asteroids known. And right now it's on in a very hazardous orbit, but its orbit evolves, and in about 150 years there's a non-negligible impact probability with the Earth for this body. This number might be a little bit old, because this slide is a number of years old, but at one point the impact odds were roughly 1 in 1800 in the year 2182. So one of the things that the OSIRIS-REx mission will do as well is to very accurately nail down the orbit of this particular asteroid, so that we can make a better prediction of where it will be in the future, whether it is an impact risk or not. And also to study the non-gravitational forces that act on this body, the so-called Yarkovsky effect, and come up with better physical models of this effect so that we can make better predictions for all asteroids moving forward. Once we arrive at this asteroid, there are actually a series of activities that we do. So we arrive late 2018, and then we carry out a period of reconnaissance. We map the surface in detail. We measure Bennu's mass and gravity field and its shape and spin state. We do all this using cameras that are on board, spectrometers that are on board, radio tracking, Doppler tracking from the Earth, imaging of the asteroid surface, LiDAR images or LiDAR maps, distance maps from the spacecraft to the asteroid. During this time period, we actually touch what we call or choose a touch and go site, which is where we will do our sampling. We prepare for that sampling in 2019 and hopefully carry it out in late 2019, and then return to the Earth with the sample in 2023. We have at least a year or so of time in which to actually successfully carry this out, should there be any issues. I'll talk a little bit more about this orbit later. So the sample is acquired by descending to the asteroid surface. And here's just a schematic for how that happens, so you can think about the dynamics of how you make this so. And in fact, initially we'll be in a Terminator orbit, which is an orbit which is perpendicular roughly to the sun. And in fact, this orbit here is a Terminator orbit. This is the view from the sun. This is the view with the sun off to the right-hand side. And you see that it naturally follows the sun. And this is from the solar radiation pressure perturbation. And for a small asteroid like Bennu, this is almost the only orbit that you could actually put a spacecraft in. However, once you get it into this orbit, it's extremely stable, and it will stay there nearly circular orbit for very long periods of time. So it starts off in that orbit, actually flies over the front of the body, has to use its LiDAR to detect where it is in its orbit, and it has to do this autonomously because the light time from the asteroid to the Earth is many tens of minutes at this point. Does a series of burns to go down to the surface, and then it touches the surface for only about 4 seconds or so. And actually expels some gas, collects its sample, and then takes off of the asteroid surface again. And it can actually carry out this activity up to 3 times in order to reliably get a sample. And the way it samples, as I just mentioned, it touches the surface very briefly, it expels nitrogen gas that agitates the surface, and actually it collects it in some traps. It was designed sort of as a reverse vacuum cleaner, where you use the gas to push things out and then you capture it. And we've actually done work on this problem from a physical science perspective. It's an interesting question how the surface of a body that's been settled in a microgravity regime actually responds to you once you plow into it at, say, 10 centimeters per second. So we've actually done a lot of modeling of this effect. And this is also a somewhat interesting granular mechanics / celestial mechanics type of problem. So as I mentioned, a key component of the mission are these orbit phases A and B at a 1.5 kilometer orbit for A and a 1 kilometer orbit for B, where we take many important scientific observations, and for us, most crucially, we make our gravity field measurements when we're in this lower orbit. So now I'm going to talk a little bit more about, or get into a little more detail about how we've designed the orbit, these Terminator orbits, in order to study and explore the environment of the asteroid Bennu. So it's maybe a little bit early for a break, so I'll just keep it going. Yeah, so up to now, this has sort of been the introduction as to why we're interested in small bodies, what we've done in the past, what we're planning to do now, and a very high view of some of the interesting dynamics that occur. Now let's talk a little bit in a little more detail about the OSIRIS-REx mission and what approach we've taken in order to analyze and understand the most important aspects of motion so we can come up with good designs. So the primary perturbation acting on the spacecraft at Bennu arises from solar radiation pressure. If you will, the area to mass ratio of a typical spacecraft at a small body is on the order of centimeter-sized rocks. So if you think about the effect of radiation pressure on a centimeter-sized rock, that's a very small effect. Yet at these small bodies, that becomes a huge perturbation and actually can cause you to escape from the system. The solar radiation pressure controls the size of the orbit that we can fly before we get stripped out, and places limits on the semi-major axis for bound motion. If we have a motion that is bound, we can actually use simple first-order averaging solutions to relatively accurately, qualitatively describe the spacecraft motion. And by analysis of these averaged equations, it actually suggests specific mission designs that we can then implement. What we find are that eccentricity and inclination are strongly perturbed by the solar radiation pressure. And for the strong solar radiation pressure effects, the Terminator orbits that I've shown are really the only orbits that are at all stable and at all flyable for one of these missions. We can also find clear lower limits on the semi-major axis, and here there are joint effects between solar radiation pressure and gravity that can strongly destabilize the motion. And there's actually been some interesting recent work done by another group where they're studying resonant interactions at small bodies when you become very close to them. So the spacecraft model we use is actually very simple. Simple SRP model, use usual characteristics of a small body orbiter. We assume we have a constant area oriented towards the sun, area to mass ratio of 62 mass to area ratio of 62 kilograms per meter squared, which is representative of the OSIRIS-REx, some nominal value of reflectance, and a very simple, in fact, the simplest solar radiation pressure model is just to have it as a constant times the distance, 1 over the distance squared of the asteroid to the sun. So on an eccentric orbit, this distance will vary, of course, and always pointing away from the sun. So here the vector D points from the sun to the asteroid. And some nominal numbers, and the asteroid orbit is given here. The specific environment of this asteroid, the diameter is about 500 meters. The density, we believe, is, I think the latest estimate is like 1.25 or 1.1, so a little more dense than this. The GM is 4 meters cubed per second squared. Compare that to the GM of, say, the Earth, that's many orders of magnitude larger. So that's another way of getting a scale for the smallness of these gravity fields. And we believe it's in uniform rotation, and the period should be about 4.3 hours. Here is actually the mapping over the surface of the asteroid of all the local slopes. And we see we have near zero slopes at the equator and at the poles only. Everywhere else, the slopes can be up in excess of 30 degrees. So the first thing we want to do is understand the escape limits. And there are a few ways of doing this. Analytically, we can derive a maximum semi-major axis for when an orbit becomes bound or remains bound. And to derive this, we can actually utilize zero velocity surfaces or zero velocity curves in a couple different ways and come up with consistent answers here. And under the solar radiation pressure perturbation, semi-major axis tends to be conserved because it's really similar to averaging in a constant potential field. So the semi-major axis can be preserved. However, as the asteroid orbits the sun, this distance d varies from the aphelion to the perihelion radius. And if this maximum semi-major axis then will vary throughout the orbit of the asteroid. And if it ever crosses the orbit that you're in, then you will be ejected away from the asteroid. And the way to come up with this limit is actually through analysis of zero velocity curves. on the left is a depiction of zero velocity curves in the elliptic restricted solar radiation pressure problem. And this is very similar to the elliptic restricted problem with some additional perturbations added in. And even though there's no Jacobi integral, the zero velocity surfaces still serve as a useful real-time limit on where motion can and cannot go. And we're actually able to use the zero velocity curve analysis to come up with a relatively precise estimate of what this maximum semi-major axis is, especially if we add it with a little bit of averaging theory. Similarly, you can consider the non-rotating solar radiation pressure problem, and this is really a variant of the two fixed center problem, where one of the centers goes off to infinity, or the Stark problem, if you will. And again, we can come up with a very good estimate of what the appropriate value of semi-major axis is, which tells us when these zero velocity surfaces open. And once they open, the probability of escaping is high, and generically, if you run an orbit long enough, it will, in general, escape from the system. So for Eros, we were able to find a maximum semi-major axis for bounded motion of about 2.5 kilometers. And here's an orbit. This is looking down on the orbit plane, and the view from the sun, chosen to be just a little bit above that 2.5 kilometers. And we started it at aphelion, where it was bound. And now you see what happens when it crosses through that, through or closer to perihelion. The orbit, which was initially bound, is then stripped off and escapes from the system. So this gives us the largest that an orbit can be. As long as we're less than that maximum semi-major axis, however, as you see, we tend to be bound at least for a few orbital revolutions, which means that that's a good opportunity for us to apply averaging theory to the motion of the body. And because of this, the semi-major axis is constant on average. The secular equations for this particular problem have actually been solved in closed form, assuming a point mass. Mignard and Henon in 84, Richter and Keller in 95, and we've generalized this to a case of an elliptic orbit around the sun. And the approach that we've taken is by using the osculating eccentricity vector and angular momentum vector. This is really the scaled angular momentum vector in order to describe the orbit dynamics. And it turns out in these earlier configurations, the solution is quite complex. However, once we jump to the eccentricity and angular momentum, scaled angular momentum, the average solution for this highly perturbed solar radiation pressure problem becomes almost trivial to solve, and we'll look at that solution in a moment. So we've been calling these the Milankovitch orbit elements because he was really the first to, I think, systematically use them in his analysis of the climate variation of the Earth. And we can use orbit elements of eccentricity vector, angular momentum, and true longitude to make them non-singular. With our scaling and after averaging, they take on a very simple form of h dot is the cross product of h with the gradient of r with respect to h plus cross product of e with the gradient of r, and sort of a skew symmetric form here for e dot. The potential form of the solar radiation pressure is very simple to state under our assumptions, where it's just that constant vector, well, even though it's a slowly rotating vector dotted with the position relative to the asteroid. And again, when you average this, as we just saw in Professor Lemaitra's talk earlier, you come up with a very simple form where the unit vector from the sun to the asteroid is dotted with the eccentricity vector. And you see immediately then taking the gradient of this quantity is trivially simple. In fact, if you take that gradient and if we rescale so that the true anomaly is, or actually the scaled true anomaly is the independent of the asteroid around the sun is the independent variable, we can actually reduce this system of perturbed equations into this highly symmetric form where this is a skew symmetric matrix. And in fact, it turns out this is a time invariant linear matrix, so we know exactly how to solve this. And in fact, the dynamics of eccentricity and angular momentum perturbed by the solar radiation pressure in this rotating frame, even accounting for the fact that it's in an eccentric orbit, is completely described by a six-dimensional orthonormal rotation matrix. That's what the state transition matrix turns out to be, controlled by a single parameter, which we denote by the angle capital lambda, which is a combined combination of the solar radiation pressure parameters, the asteroid orbit elements around the sun, and the spacecraft orbit around the asteroid. And what we see is for a very strong perturbation, this lambda goes off to pi halves. This gets arbitrarily large. Weak perturbation, lambda goes to 0. This becomes very small. The Hayabusa spacecraft at Itokawa would have had a perturbation angle of about 87 degrees, telling you that it's highly solar radiation pressure dominated. Near at Eros had an angle of only 13 degrees, and that was really gravity dominated. The solar radiation pressure was a minimal effect. OSIRIS-REx at Bennu is 85 degrees, which is still quite intense. And if you tangent of 85 degrees is actually quite a relatively large number. So, linear time invariant system, we can express the solution like this, and it's really just a 6x6 orthonormal rotation matrix, periodic in true anomaly, with a period of 2 pi divided by cosine of this lambda. So what happens if lambda is very large, close to 90 degrees, cosine of lambda becomes very small, and this period gets very long in terms of, or the period in terms of true anomaly tends to get very short, actually. And we can actually write out the solution very simply here, defined as a function of scaled true anomaly. So when this is equal to 2 pi, the true anomaly has moved 2 pi times cosine of cap lambda. So the stronger the perturbation, the shorter the period that the solution repeats itself. So a 1 kilometer orbit will have a secular period on the order of 38 days. It tends to be faster at perihelion, slower at aphelion. When we study these equations, it finds out we can find relative equilibria to them. There are actually 4 different relative equilibria. Only 2 of them are relevant for us. And these are the solar plane of sky or / Terminator orbits. And these, in fact, are orbits which, on average, remain constant when you start a spacecraft in them. They have an eccentricity, and an interesting result is that the stronger the perturbation is, the more circular these orbits become. So as the environment becomes more and more strongly perturbed, the orbit that you need to fly becomes nicer and nicer, because we always like to fly circular orbits. Right. And this is sort of a graphic representation for a weaker perturbation, where you have a more eccentric orbit. These have very specific relations on the nodes and the argument of periapsis. The arguments of periapsis either have to be below or above the orbit plane, and the angular momentum of the orbit has to either point towards or away from the sun. And those two happen in certain combinations. For Bennu, we find that orbits much closer than 0.7 kilometers, and we can actually estimate what this radius is using some other analytical methods. The gravity field will actually start to destabilize the motion. So here's an example of our orbit phase B, a 1 kilometer orbit. This is a 1 kilometer circle, and here we started 2 of these orbits, one pointing away from the sun, the other one pointing towards the sun. Starting them with the frozen orbit, and this is fully numerically integrated for about 1 year, 1 asteroid year. looking from the sun all the time, accounting for the full gravity field of RQ-36 and the eccentric motion of the asteroid about the sun. So we see that they're actually quite stable. If we just drop the orbit down by 500 meters, we see that over time, at least one of these orbits becomes quite unstable and actually impacts onto the surface. And here this eccentricity is chosen at this orbit radius so that these are placed in the frozen orbits. You can do a lot of other interesting things with the solution. In fact, we're still studying some other applications of it. In fact, this solution can actually be used to describe the orbital dynamics of a high area to mass ratio piece of space debris in orbit about the Earth. And that's another application of this particular solution that we're studying currently. I won't go through this in much detail, though it is interesting to note that it's impossible to have a constant zero eccentricity solution. This guy, when you started off at a zero eccentricity, and since it's periodic, this represents any orbit that ever goes through a zero eccentricity, there's no way you can choose the initial angular momentum to force this guy to always be circular. In fact, initially circular orbits always have a very specific one-sided oscillation in eccentricity coupled with oscillations of the plane out of the Terminator plane. Here again are 1 kilometer initially circular orbits away from the sun and towards the sun, and you see that they grow only in one direction. This is again run for over a full year, so many oscillations of the eccentricity. And again, if we start a little bit closer, it doesn't work, and this guy impacts. This is the orbit geometry I was just talking about. I won't go through it in detail, though. This is something we get directly from the solution, is sort of a map of the motion that we see in the vicinity of the Terminator orbit. And what I have plotted here is the longitude of the ascending node versus the eccentricity of the orbit. And this is just really mapping out the initial conditions analytically for that linear equation that I had shown earlier. When we're at a 90-degree longitude of the ascending node, we are in fact face onto the sun, what we call a Terminator orbit. And we can see the whole range of solutions mapped on this one diagram. If we're at this point, this is the frozen orbit, and we will nominally stay at 90 degrees at whatever eccentricity that frozen orbit is defined for. What I just showed in this previous plot, these circular orbits, is actually described by this condition here, where I'm starting in the Terminator plane at a circular orbit. And this guy is just tracing out a quasi-ellipse, and it goes to a higher orbit. It comes back to its periapsis, which is at the initial semi-major axis of that circular orbit. If we increase the node, or if we sort of sample a larger parameter space, we actually get motion that moves across here. It goes through a circular orbit, crosses at a lower eccentricity, goes through a circular orbit, and repeats this pattern. And we can see that if we start far enough out of the Terminator plane, we can get arbitrarily close to a unity eccentricity for our asteroid, or for our spacecraft orbit. And of course, we want to stay away from these because these would be impacting on the surface. But this is a very simple result that comes out of our analysis that we can use to map out how we can design, appropriately design orbits around this particular body. This is just a numerical integration of this particular orbit, showing the variations in the longitude of the ascending node, the eccentricity, and the two plotted versus each other. And we see that behavior when it crosses 90, it's either at one of two extremes, and it goes through 0 when it goes to its largest Terminator crossing. And in fact, we use that particular result to specifically design these orbits that we will be flying for the OSIRIS-REx mission. And in fact, as you see it now, with maybe a closer eye, you see that this orbit does oscillate from circular to eccentric. As it does so, the orbit plane also oscillates in and out of the Terminator plane. And this is a fully numerical integration, but what we see matches quite closely to that very simple linear equation that we were able to derive for the motion of this particular body.